Thank you very much. Hi, I'm Bart Massey, and I'm sorry for fouling up the schedule of the conference with my presentation with all the weird audio and stuff in it. But I wanted to talk to you today about something a little different than I think these kind of conferences have sometime. I decided it was time for me to give a talk that had some fun tech in it. So we're going to talk today about some principles and about how neat Rust is. We're also going to play around with some hardware and understand how things work a little bit in the embedded world, I think. So yeah, I'm a computer science professor at Portland State University in Portland, Oregon in the USA. I've been there about 25 years. I started doing embedded stuff in the late 1970s and was employed for a while for Tektronix to do embedded audio stuff. It's one of my favorite things to do in my spare time. I'm a computer science professor. I teach all kinds of things. Many of them are Rust. But one of my favorite things to do in my spare time is to mess around with embedded audio hardware. So before we start, I want to thank a bunch of people. I want to thank the GoSim folks. I'm sorry your logo didn't get on the slides, but for inviting me and for making it possible for me to be here. That's fantastic. And the Rust ChinaConf folks. I wanted to thank the Rust Embedded community for being incredibly supportive of the things I've done over the last few years. I wanted to thank FutureWay, who's provided me with funding and sponsorship for a thing I'm running called Rust-Edu. Rust-Edu is my attempt to try to bring Rust into universities, and I'm trying to put together an organization. I would love to have your help with that. So, with that said, here's my message. Here's what I want you to remember from today. It's about me, but it could be about you too. Rust has absolutely changed the way that I prototype low-level things in a way that is absolutely been revolutionary to me. Like I say, I've been doing this for many decades, and now I do it a different way. And it's a much, much better way, a much, much happier way. So I want to talk a little bit about prototyping and what that is. I guess first, a little bit, yeah, I mean, the industry's done stages, right? And I've done stages along with them. 6502 assembly, 8080 assembly, 56K assembly, C, Unix, you know. This stuff has been hard, but it's also been really fun. And as it's gotten easier, which it has over this time, it's gotten to be even more fun. And so I want to talk to you today in particular about sort of what the depths of the Rust stack looks like. Rust is a bare metal language, woohoo, it's a low-level systems programming language, woohoo. And I know that a lot of people in this track are interested in the AI and the higher level OS things, but I'll talk about that. But I also want to talk about the thing that sort of is Rust's easy case, the case of actually building low-level systems. I want to talk a little bit about prototyping, what it is and what it does and how it works, because I think that's an important thing that we don't talk about enough in university at least, and I think even in industry, it's easy to what a full tool a prototype can be, and so I want to talk about that. And then I want to talk to you about a project. It's been a spare time project of mine for the last several years that is sort of my white whale. If you know the story of Moby, Captain Ahab is forever chasing the white whale. And this is one of my white whales, is this particular project that I'm trying to solve. And finally, I want to talk about how all this stuff applies to sort of industry-ready or real-world projects. So, yeah, in the modern world, down below, we have this stack. And it's a pretty deep stack. And Rust has even added layers, I think, to that stack. So there's a lot going on down there, a lot more than there was in olden times when, you know, there was the operating system kernel and there were some device drivers written in some combination of C and assembly. And that was pretty much what you did. And if you were writing embedded stuff, you wrote in assembly. That was a thing at a time in the past. We now have this stack that's really, really interesting. Clear down, you know, next to user land here is the operating system kernel. In Rust, that might be something like Redux, but most operating system kernels today are written in some other language because they're old. That's closer to where you are. But down below that, you might instead, for embedded stuff, use something called a real-time operating system, an RTOS. And there's 1 billion RTOSs in the world. In Rust, we have things like Talk. In the rest of the space, we have things like Zephyr, which works really nicely with Rust. People use a lot of other things. And the conventional wisdom, I think, in current year is that you have to have an RTOS. That if you're going to do any serious-sized embedded thing, that means that you're going to get a real-time operating system and you're going to get it running. And sure, you might write some Rust for the low-level stuff, but of course the RTOS does all the real work. The cool thing about Rust Embedded is that just isn't true for us. We give you options that you wouldn't have otherwise. Arctic and Embassy are 2 examples of what we call a runtime in Rust. What's a runtime? Well, it's not really an operating system, but it's more than just nothing. It provides the ability to do timing, to do timed tasks and to give some implementation of concurrency to handle interrupts, to do a bunch of the things basically that make a larger embedded project work without needing an operating system. Operating systems are great, but they're also a pain in the neck. They mean that you're doing a lot of weird abstraction stuff that if you need it, but you normally don't. And so Embassy in particular has been kind of a game changer that's very Rust specific because it uses Rust's async await to do, honestly, the coolest way to use async await, to do interrupt handling and that kind of stuff and give you a task system with no operating system underneath. That's pretty cool. Below that, we have a platform layer, and this is an architecture that many operating systems have had, in the past, of a sort of a platform board support package, they call it in the industry, that provides for a particular piece of hardware some tools for dealing with that hardware at a high level. I was going to wave around, but now I've misplaced it in all the confusion. I have a couple little microbits, and I'll talk about those in a second. Here's one of them. And that thing, this is a little board. It's got some hardware on it. We have nice abstractions in Rust or in C for dealing with this. Below that, we have the HAL layer that sort of provides a thing that's independent of a particular platform. We have a peripheral access crate layer that's below that. And then below that, we have just good old bare metal like we used to write in the olden days. Rust will do all of these. Across this entire stack, Rust is a useful tool, and that is a crazy thing. It is absolutely vital in playing around. Yes, like I say, I'm going to talk today some about the BBC microbit. This is a board the British Broadcasting Corporation did for teaching kids using microcontrollers, boards of all things, in really high-level languages, blocks programming or Python programming. And it's got a little computer on it, and it's got a whole bunch of fancy hardware on it that is really cool to use that way, for literally very young children. It also turns out to be a good target for Rust. And our Rust introduction to embedded Rust is something called the Rust Embedded Discovery Book. That's the link to it down on the bottom. I'm currently the editor of that book. And that's the target we use. That's what we use because you can get them for US $15. And they're great. They're available everywhere. They've been available for a long time and will be available for a long time. They're a great teaching tool. So I want to talk specifically. Oh, and before I do that, I want to talk a little bit about prototyping, because prototyping is super important, and we don't talk, I think, enough about it, like I said at the beginning. What's a prototype? Well, first of all, anybody who's trying to do real engineering without building prototypes probably is going to fail. It's absolutely an important part of this whole process, and you can't do without it. But the thing that people miss about prototypes is prototypes aren't especially in software and hardware engineering, prototypes typically aren't something you want to then put into your product. Prototypes are what we use to learn things that we can put into our product. A prototype is for gaining knowledge. That's what it's for. And ideally, at the end, when you've learned whatever you need to learn by building your prototype, you throw the prototype away. Disposable prototypes are the best prototypes, right? You might save a little code, but mostly you keep your janky prototype code, whatever it was, out of there because now you know what you need to know. And so I want to talk a little bit about a prototyping exercise that I've gone through here. This piece of that, this is on the microbit board that I showed you earlier. On the back here, that biggest thing, you might think that's the CPU. No, that's a speaker. That's for producing sound. And it's actually a pretty nice speaker. I've used it in other projects, and it's an actual magnetic speaker in that tiny form factor. And so it makes pretty good sound if you drive it right. How does a speaker work? Well, you probably know, but just in case you don't, a speaker works by pushing air in and out. And as the air is pushed in and out, you get high pressure air and then low pressure air, and so it travels out away from this. So right now I'm being a speaker. That's what I'm doing. I'm being a speaker at such a low frequency, at such a low rate, that you'll never be able to hear it, and it won't even travel through air very well. But if I could do this at 1,000 times a second, then you'd have something. Then you'd hear a noise. And that's exactly what the speaker does. On this speaker, on the microbit speaker, there's this little port over here that the air comes out of. And that little teeny port is what's producing all the sound that comes out of this. This is a piece of electronics. You are not expected to understand this, as the old thing goes. But for the few of you who might know a little electronics, basically we put electricity in right here. This is a switch that switches the speaker between being all the way out and all the way back in. So when the microprocessor says, speaker go out, it goes out as fast as it can. When it says, speaker come back, it comes back as fast as it can. And that is how you make the speaker go back and forth really fast and make a noise. This speaker driver circuit has an issue, and it's that issue that leads to my little challenge here. This speaker driver circuit has no way to smooth that out. Real sound, like speech or music, you move in and out, all different ways, right? You need something very controllable. You can't just do this. If you just do this, all you get is a square wave. And a square wave is fine. You can make a tune with it and stuff. But unless you smooth this out into something that's better, then you can't make very interesting sounds. Here's the thing. To my knowledge, no one has ever gotten this board to produce speech or music out that speaker because the speaker circuit's wrong. And so my plan, which I've been working on for several years and cannot report success on yet, is to do that, to be the first person to do that with this hardware. And so the rules are I'm not allowed to modify the hardware, but anything I can figure out to do in software, that's okay. We will do that thing. Whoops, I don't know what happened there. And I don't know what's happening here. There we go. So this is, I'm going to show you the, ideally, the tutorial. Like I say, the Rust discovery tutorial for the microbit. At the end of the chapter, we do this. We upload code to the little microcontroller, and that code we upload makes a nice siren noise. Excuse me for the siren. So I'm going to run this thing, and it's going to do that. It's going to count down for 10 seconds, and when it's done that, it will print a little message, and that'll be the end of the demo. I hope that wasn't too loud. But yeah, that's an example of what you can do real easily with the microbit, and that's where that chapter I just wrote in the discovery book stops. That's fantastic. Oops, no, I don't want to do it again. I just want to go on to the next slide. Come on, you can do this. There we go. So here's a different example. So now what am I going to do as I try to manipulate that sound card more and more, hardware more and more? I'm going to prototype, right? I'm going to try stuff and see what works. Let me show you another thing that, as far as I know, nobody's ever done until I did it. I mean, maybe somebody has, but I haven't seen it. This is sound with a volume control. It's still square waves. It's straight in and out. But by using a trick called pulse wave modulation, I messed around with a bunch of Rust and was able to figure out how to do it in such a way that I could make louder noises and softer noises. You can see there on the graph, you know, the louder and softer noises. That's a measurement of the audio. And if you listen to it, you'll hear it change volume. So yeah, you hear those 3 different volume levels in that thing. And I have a Rust game audio library up that uses this to if you want to make game sounds for a microbit. But it's still all square waves. It's still all gross. We don't really want that. So here is sort of where I am with my prototypes right now. I've tried to go ahead and use PWM to make a square wave that's an example of making things more controllable. The bad news is you can see that that doesn't look on that signal graph there very much like a square wave. It's still wavy. So I'm still prototyping. I'm still trying stuff, trying to figure out what's going on. The goal is speech. Let me play you the best thing I've ever done as far as getting speech out of this speaker. So that was recorded using a very sensitive reference microphone because it's very, very quiet. And I'm sure you couldn't understand what that said at all. But it does sound kind of like speech. Let me play you what it actually, I'm going to turn the volume down a little actually, but I'm going to try to play you what it actually is supposed to sound like if it was good.
Hello, this is Linus Torvalds, and I pronounce Linux as bloated.
So that was what it was supposed to say. And if you listen to it, you can kind of hear that, but I haven't figured out how to make it right yet. I'm still prototyping. How do I know the microbit can do this at all? That little circuit there has literally 2 components, a resistor and a capacitor. That smooths the output of the thing. So I'm doing the exact same software, driving out an external speaker and into an external amplifier. And when I do that, it sounds like this.
Hello, this is Linus Torvalds, and I pronounce Linux as bloated.
See that? I know it can be done. I can smell it. It's a thing I really can figure out how to do, and yet somehow it's just still out of reach. So let's talk about why I'm doing my prototyping in Rust, and why Rust is such a great language for prototyping, why I care about doing this project this way. First of all, even more than regular code, when you make a mistake when you're prototyping, it's really, really bad. Because when you make a mistake prototyping, now you don't just have code that doesn't work the way you want, you've learned the wrong thing, or you've failed to learn anything, right? I'm now more confused than I was before I started prototyping. And so bugs in prototype code are awful. Hey, guess what Rust is really, really good at? It has both really good compile time checks for stopping that, and at runtime, it actually catches stuff. C has no runtime checks. Mostly people would write this in C, and the lack of C runtime checks means that things just behave weird when you're messing around with code on these little microprocessors, and nobody wants them to behave weird. You have a full ecosystem at your fingertips. Crates.io works fine in the embedded space. If I want something like a thing for a knob or something like that, a software to deal with a rotary encoder or something like that, I just install a crate from Crates.io. It's literally no different than in the high-level world. So that's kind of fantastic and a very different experience than any other embedded world I've ever lived in. I can talk as directly to the hardware as I wanted to. I don't have to be behind an abstraction layer, but I can have one if I want to. there's just like any other low-level language, I can just go mess around with device registers and stuff like that. It's Rust. It doesn't care. And that's fantastic. I can write inline assembly. That's fantastic. So what I get is leverage. When I'm prototyping, I spend my time actually learning the thing I'm trying to learn, not messing around with the language and the ecosystem and the tools. And that is just so much nicer. Of course, this is the AI and OS track. I should talk a little bit about how I use AI in embedded prototyping, because I do. I've found that it's really, really useful. And yes, large LLMs can write embedded code. They're actually pretty good at writing embedded Rust. I'm surprised how good they are at writing embedded Rust, honestly, and sometimes it feels like they're better than my students, maybe better than me at writing Rust. But that isn't the primary way. When you're prototyping, the code is usually small, and it's not that hard to write. Your time isn't spent churning out code, miles of code, because you're not doing production. Your time's spent figuring stuff out. And so where the AI really shines is if you want to do find out about something, or if you want to tutorial about something, or if you want to figure out how some piece of hardware works, or what's going on in some manual you don't even know where it is. That kind of thing is huge, huge power, because it means that you can do sort of blue sky stuff instead of spending all your time Googling around on the net. I tried, and I was going to show this off. So I tried DeepSeek and Gemini Flash just at random as two free things, and asked it to describe the speaker circuit on the microbit, which I'm afraid it was worse than anything I've ever tried to ask it in the embedded space. So I thought it was funny. I'm not going to try to show it to you, but I'll tell you what it says. DeepSeek is like describing the hardware of the speaker hardware of the microbit 2, and it sounds fantastic. It's got a fancy audio amplifier and all this, and a DAC on the microcontroller. It's all just hallucinated. It describes the hardware I wish I had. The Flash isn't so great either. Flash was telling me about how the hardware was connected, and it was just completely wrong. So you do got to watch out for the hallucinations. But if you just start knowing nothing, you can at least get some stuff and then check it later. Refactoring of code. I find that if I have code that's all scattered and messed around, it's really nice to tell a large LLM to go rebuild all those pieces and glue them back together in a way that makes sense. That's the kind of thing they're very good at, and the kind of thing that for me would just be hours of tedium. Eliminating tedium best. Oops, I don't know what happened there. Code review. It's surprising how good they do at that. If you're building operating systems, this Rust layer allows you to either avoid OS with an embedded runtime like Embassy or Arctic, or it lets you build your drivers on top of a whole bunch of cleanly tested Rust lower layers, and that's pretty fantastic. And the thing is that even if I'm building discardable prototypes, I plan to throw away the code, I still get the patterns and stuff that I need to write operating system kernel code that actually works. So, yeah, that's my message. Rust is absolutely great for low-level prototyping. It plays well with others, and I can highly, highly recommend it. I know this is a weird talk for this track, but I hope that you had some fun, and I hope you learned some things. So I think that's what I've got for you today.